Hello, everyone. Welcome to PyData Global 2021. I'm Conrad, one of the co-chairs of the conference. We're happy today to have Meenal to come talk to us about hierarchical Bayesian models in PyMC. PyMC. Thank you, Meenal. Take it away.
Yeah. Okay. So hi everyone. So I hope you're all doing all right. I mean, as well as it can be given the pandemic and everything. But yeah, thanks for coming. I mean, I understand that it would be difficult to attend virtual conferences, and thanks to the PyData team for organizing. I mean, they've had to work so much. So let's get started. So today I'll be talking about deconstructing hierarchical Bayesian models using the library PyMC. And all the slides in the code can be, it's in this repository that you can check. If you want, I can drop a link later in the chat as well, if you don't find the repository. So a bit about me. So I'm an undergrad student in my junior year. I'm from India. And this summer, I worked with PyMC 3. Back then, they were PyMC 3. Now we're releasing a new version, PyMC 4.0. which so yeah, the 3 is gone. So I worked with them over the summer. I was working on extending time series models, and since then I've been working with those folks, and it has been really amazing. And by the end of this talk, I hope I can convince you to maybe at least try PyMC if you haven't already, and if you have, then well, maybe use more of it. These are my contacts in case you need to reach out or anything like that. Okay. So let's get started with it. So now I planned for this talk to be, very accessible. So if you haven't really been introduced to Bayesian inference before, I mean, I cannot really sum it up in a slide, but it's basically just that, say in frequent statistics, you have these, you just count up that, okay, this is what happened. And this exact number is the frequency of this particular event happening, and they're basically interpreted as long-run frequencies. So the goal is to create procedures with those long-run frequency guarantees. But in Bayesian statistics, the probabilities are interpreted as subjective degrees of belief, and the goal is to state and then analyze your own beliefs. So yeah, you basically have some beliefs and you update them, and then you get your posterior distribution. And this is where probabilistic programming languages are very useful, because okay, now you might ask me that what are probabilistic programming languages? So there's this talk of Chris Fonnesbeck in PyData, in one of the PyDatas, and he said that, okay, it's basically just literally any language where the overall outcome that you are getting is not deterministic, and that's it. I mean, you have distributions, you don't have a deterministic way of doing things. So you can do probabilistic programming in any language which has a random number generator. This figure is from the architecture file of PyMC 3. And so you would get sort of an idea of how the API works. We have samplers and we have all distributions bracketed into continuous and discrete and processes. And yeah, I mean, right now a new change is, earlier the backend was Theano, now it has changed to SRA, which we're hoping will make it easier to use PyMC3 for you. Okay, so moving on. Today, what we're going to talk about is hierarchical modeling. Now, that just sounds like a fancy term. You can build it in a very bottom-up approach from linear regression itself. So first, I'll just tell you about two of the important terms that we'll be using when we talk about hierarchical modeling, and then we'll see, what it actually is. Okay, so yeah, I mean, they're really just sort of simple ways of saying, okay, you have a probability distribution, and now the parameters of that distribution are itself derived from another distribution. So yeah, that's the hierarchy. This is one level, and the priors for this distribution are another level. So now this is just an example of a two-stage hierarchical model. So say you have an observation y and you have a parameter theta that governs the data generating process for y. So now you assume that all the thetas are generated interchangeably from a common population, and the distribution is governed by a hyperparameter phi. So there are like 3 stages in the hierarchical model. First, from y, you have the probability of y when given theta and phi, and then theta given phi is the distribution, whatever we specify, whatever priors we get. So yeah, this is like basically your priors and posterior and likelihood all combined, just with a difference. Like this is Bayes' rule with just one difference, that we have another parameter phi or theta, whichever you want to take for the original prior. That also is, we're getting that from another parameter. That's like the only difference. So now I thought that before getting to the final model that I'll be presenting, we can like make little dummy models that are like, we won't be thinking too much about what parameters to get, because we don't care about the results in those moments. We just want to see, okay, how does it even work, or how am I going to do this in PyMC3? So say you have these predictors that, say we took 2020's data, and now we want to predict that how are the players going to play in 2021. And so you take 2019 scores, or you take 2020 score, and you multiply that with some coefficient, and you also know that, okay, maybe their position might have some effect. So you can do this in a couple of ways. That's where we'll realize that when our hierarchical model is relevant. Turns out in a lot of places, they're not useful, and using them is sort of counterproductive. But yeah, that's for later. So, I'll just get back to the slide after this one. All right, so you can see this. So in complete pooling, that's just a term. What it really means is it's just basically linear regression. So this alpha is the only term we should be thinking about. That, okay, we're predicting these things, and there's Gaussian noise, and X is the previous year's points. But the thing is that for position, we are assuming that whether the player is a forward or a goalkeeper, we don't care. They're all gonna, that is not gonna create any influence about how the data will change. Now, okay, if it was a situation where it really wouldn't create any difference, we could use a simpler model, because we prefer simpler models. But in this case, this isn't really a good idea. We'll see next. So this is just how do you just build this in PyMC3. So yeah, this would probably give you an idea of the syntax or how you write code in PyMC3. And so yeah, you just give your data as an array, and you give your points. You say that, alpha and beta and sigma, just like we had over here, are distributions. Given your specific data, you should think a lot about your priors, whether the variance is too much or too less, or whatever you're doing. And PyMC3 also has this PyMC. I'm still getting used to the fact that 3 is removed. So it has this cool thing where we can get these graph-based diagrams right after building the model. So it's easier to visualize and understand what's going on. So yeah, we see that this data goes in, and this is what we want to predict. So yeah, this is what we did in a completely pooled model, but turns out this isn't a good idea. Another option, which is on the absolute extreme, is unpooled models, where we say that, okay, we should have a different distribution for every single player, as in forwards are a whole different category and midfielders are a whole different category. But like there are obviously quite some similarities as well. So this extreme doesn't really work as well. In a lot of cases where the groups are not that rigid. So in those cases, this isn't a very, I would say, good thing to do. Again, the only change that we did in the syntax that was mentioned previously is in alpha, we simply gave, so PyMC has these things called shape and size and dims and quads. So which are basically for specifying that, okay, I mean, most of the computation goes on in high dimensional arrays. So so you're basically having all these matrices and you want to say, okay, how many rows do I have? How many columns do I have? So similarly, DIMs are just another one of those things. And we're saying, okay, we are calculating a different alpha for each of the position values. And we gave position over, okay, the coords line is not written here. It's basically you give coords as a dictionary where you encode the positions as say 0, 1, 2, and 3, each for forward, goalkeeper, defender, midfielder, whatever you're taking. So yeah, again, we have a nice little figure over here to see what's going on. I mean, I think I'm going a little fast maybe. But yeah, I just have a lot of slides and I just want to go through them and see if I can explain something meaningful. So then comes partial pooling. Now, Andrew Gelman in one of his books describes it as, it's this compromise between unpooled models and completely pooled models. As in, we're saying that, okay, position does create a difference, but yeah, I mean, they're all still football players and they're, I mean, yeah, we should probably be having some similarities between them. So we take one distribution from which we take multiple alphas, alpha 0, 1, 2, 3, and we use those for all the different positions that we have. Again, we have this figure. Now, this figure is really different from this one, as in, so yeah, we're giving last year's points and we're giving position data. And here is our alpha. Now over here, what we're doing differently is first we have an alpha as we gave previously without the dims. Then we have another parameter, alpha position, which is basically something that whose mean and variance, mu and sigma, because it's a normal distribution, is from the previous alpha that we gave. So all of them, I mean, all of them have some sort of a similarity. So yeah, that's now we can probably get to, building the actual model. So over here, I've just taken all the slides from my Jupyter notebook itself, and I'm just going to quickly run through them. So I'm someone who thinks that, the data you get kind of really matters for whatever models you're building. I mean, I'm not the only person to think that, but yeah. So now there is this repository that I'll probably add a link to in my notebook as well, Fantasy Premier League, which has all this data. And so I just took 2020 and 2021's data from there. And okay, yeah. What's wrong with my slides? Okay, yeah. So now, because we want to use 2020 and 2021's data together, as in we want to take some parts of, so by previous year's points, I meant that, okay, this particular player in this game week, what were their points at that point of time? And we use that as some sort of an estimate of that, it has to be something slightly larger or slightly lesser than that because of some factors, maybe the fixture, maybe the opponent they're playing against, something like that. So yeah, we take the same players because, yeah. And then, we just add those total points in the new database, as in the original one that we'll be using. Now over here, we had to, like all that one hot encoding stuff and everything. This is not that. This is just saving all the teams as numbers. Now, another thing that I did was like, okay, we'll take last year's teams total goals and goals defended and teams that won and everything to sort of cluster all these teams into, say 4 categories, that these are like the best 5 teams, then the okay 5 teams, and the 5 worst teams in this particular area based on our prior knowledge. And this is something that is always emphasized in Bayesian statistics, isn't that, yeah, I mean, your domain knowledge is something that is very relevant when you want to say that what kind of predictions we're trying to make. So we took that, and yeah, from those, we just made these clusters where the ranks were out of from 1 to 4. Now, this idea was originally in a paper. I have no idea about the name, but yeah, it is mentioned in the references of this presentation itself. So they took a few of these clustering things in only one parameter, I think. They just took the final team wins as a parameter. So I was like, okay, maybe we can do something for defense and attack as well. And we did that. The Jupyter Notebook slides came out really weirdly for some reason. I converted them to PDF. Yeah, another parameter that I took was the initial value that, all the players are given at the beginning of the game weeks, as in, okay, this particular player is valued some $1 billion, etc. And that would, again, give us some domain knowledge that we don't have the capabilities to model, because like obviously that would say a lot about their entire previous history. And so we took that. Now that is something that we'll just be multiplying with the coefficient, because we don't really know how much is that supposed to affect. And then yeah, we one had hot encoded the positions. We took the game average of the previous year. This is 20, and our original data set that we are training on is of 21. So by 20, I mean 2019 to 2020, that season. And so yeah, we took the game average, difference from average ranks. So like, yeah, we have a bunch of ways to say how did a player perform in a particular game week to train our model. Now, once we have this, we took the home and away data. Now that is something that, I think almost all sports analytics models take. So now we'll build a model. Now, I have something to say that this isn't a very good model. It can be a little useful. Yeah, I'm paraphrasing a famous quote. It's okay. So it can be somewhat useful in understanding how hierarchical models should be built, or what can be better ways to build models for predicting football stuff. But yeah, let's just get to it. So I'm using the development branch of PyMC, because I wanted to see that, how is it working and everything. And a few features are still missing, but we'll be releasing an alpha or a beta version really soon. So yeah, look out for that. That's going to have a backend of SRA. So we took all our data, we split it into train and test. And now this is one of the few priors that we took. So if you're like not familiar with Bayesian statistics, like this new -1 thing is basically that from the paper, Bayesian estimation supersedes t-test. So they use, in general, we use student t distributions when, it's like a particular version of a normal distribution when you wanna have like heavier tails or something. So in those cases, priors are something that actually are very subjective, and there's no real way to say these are good priors. But yeah, you try to incorporate as much knowledge as you have. And if you don't, then you shouldn't be informing that, because that will definitely make your model worse. But yeah, flat priors, again, worsen your computation time. So it's like basically a very thin balance line. Now, this is how you insert data in PyMC. That is something that we already did, I think, in the previous models. So yeah, you gave all your data. This is the only data that we'll actually be using. These clustered ranks that I told you about, the initial value, home, and average scores, their teams, and their one hot encoded positions. Now, so yeah, this is where your hierarchical stuff begins. So this is, say, we want to measure the opposition's defense strength. So we take a particular distribution for that, and then we say, okay, now this will have different effects on the forwards, right? And different effects on the midfielders and different on the goalkeepers. But the overall strength of the opposition's defense will play a factor in all of them. So we're accounting for the similarity and the differences. So yeah, similarly, we do that with home and away and split that into, these 4 positions. Okay. Yeah, this is the same thing as we did with the opposition with that particular team strength. I mean, this is something, so a significant portion of this model is from a model somebody had built, which is again in the references. And I was thinking that, okay, if opposition has such an incredible part or whatever, I mean, we don't know if it's incredible, but yeah, it would play a crucial role. Similarly, the team's strength itself is going to play a role. I mean, yeah, if you have people who are passing properly or everything. So yeah, I mean, the same player in different teams would play differently. So yeah, we took that. And now it's like we split the opposition's strength into defense and attack and team. And yeah, these are just those. I mean, this gets very big. And that is probably one of the things that are not very good about this model. I mean, there's a fair chance a lot of these parameters are, you would say, one of them is taking into account the effects that the other one is trying to predict. So they're not really useful, and it would probably require more domain knowledge and more testing the priors, because most of the priors over here are like almost similar to flat priors, because I do not know enough to say that, okay, this is the prior I should be taking. So yeah, I took these very vague priors. And yeah, finally, we evaluate one of the first likelihood. There'll be 2 likelihoods. The first one is we take the defensive strength to account for the difference from average, like as in the difference from the average of the previous 7 matches. Like that is what we expect that, that is what the player should be scoring. Maybe like in 2020, in 7 matches, this was their average score. So in 2021, it should be somewhere near that. So we think that, okay, maybe the teams they played against were better, or worse, which caused the difference. So we do that. And then we add up all the other teams, the player wise, the position wise effects, depending on the team that they were in. And we evaluate a second likelihood so I don't know if you've used Stan or one of the other probabilistic programming languages. I mean, there are a ton, and many of them are like doing great work. But I think one of the things I like about PyMC is that it's like sort of really easy to, just put in things like I just mentioned, observed as this one thing. And but that's probably something that is easier in Python, and the cost we pay is that the computation time is higher. So yeah, it's a balance. Now this sampling took 30 minutes, so I just saved the trace. The trace is basically the data we're getting from it. I mean, all the samples that happen. So this is saved, and I just loaded it. And yeah, this assert, the result isn't in this presentation, but the R hat was not nice. It was like 1.4 or something for some parameters. So yeah, not a very reliable model. But what we want to say is, okay, does it work at all? Now, okay, we'll just try to test it on our test data set. So we had 44,000 samples in the initial posterior that we were evaluating. So we have again 44,000 samples. Now, one of the things that I did here that you might have noticed is I used Metropolis, which is not a very reliable way to sample. It's just that it was taking like really, really long to samples. And so yeah, Metropolis was somewhat faster in this case. But if you're using something for, production or something that you want to deploy and you want like more reliable results, I wouldn't really advise doing that. And yeah, so this was basically the number of players in like 15 among the actual top 15 players in those leagues and the ones we predicted, and we had like 7 in common. So which is like, all right, we got some of the players now. I mean, I don't think these statistics matter a lot. What really matters are like the trace plots that you generate from, I mean, not just trace plots, I mean, all the ways that you can diagnose that whether your model is working really well, or is it just, is it just a random stroke of luck that you got some values right? Is it reliable enough? So like a few days before this, I was just finishing up the model and I was like really struggling with it. I started really late, and so I was talking to a few of the folks at PyMC, and I was like, okay, I made these mistakes and I have no idea what am I going to do. And so they were like, okay, maybe people can learn from your mistakes and, bad modeling choices. So one of the few things was when you try to generate trace plots for this model, you get about, since there are like 25 or 28 random variables, the whole plot is not even viewable. And so I just didn't really put it here. But yeah, there definitely is no reasonable conversions. Okay, 5 minutes to go.
Yeah.
Okay. Yeah. So yeah, these are players you predicted. And I don't watch a lot of football, but I think it's like all right. So these were the references. Okay, I really wish that you would read this notebook. It's like the link I put is the updated version. I mean, the docs currently in PyMC are in sort of 3 versions: the stable one with PyMC 3 documentation, and this is the latest one. Now, this has this basically sums up like multi-level modeling as a whole concept, as in when you start with mixed models, you vary intercepts, you vary slopes and partial pooling, and with proper figures in everything. And I think that'll be really easy to follow. So I think you should check that out. And now I guess if somebody has questions, I'd be happy to deal with them.
I think there's a bunch of questions in the chat.
Are we predicting the full season or N weeks ahead? And similarly, are you measuring performance only up to the full season? No, I am not predicting the full season. So I just use the 2019 to 2020 data as for getting the 7-week average of the 2020 to 2021 season. I mean, so I'm just predicting like up to the first half, like out of say, how many game weeks are there? 38, like probably the first 19 game weeks. And one thing that I do is that I eliminate some of the players who have really low points because they tend to skew the entire distribution. Players who have played for only a few minutes or something like that. And yeah, I mean, I only use minutes played to eliminate some players, nothing after that. And how does it compare to these odds and the massive data model that is used in the community? I have no idea. I did not compare. I did not do any cross-validation because I did not find similar models on this data set that were working. So yeah, nuts. Yes, nuts. In PyMC, we use nuts.
Cool. Thank you for your talk.
Great, thank you.